Yeah, let's go ahead and get started.
Yay.
Great. All right, so this is computer architecture. Is anyone not supposed to be in this class? I've actually had this happen before.
Seriously?
Yeah, students like, oh wait, this is computer science? I'm like, and then they're like,
I think the computers gave it away.
What?
That was what their Java
yeah, that was the
class.
Java class. Like, this is Java? I'm like, whew.
start.
But what's funny is he didn't realize it until about 30 minutes into
Yeah.
it.
He was like,
30 minutes
Yeah,
in.
so- okay.
and then he got up. He was at least funny about it though, so.
It's really awkward though. I hope the other teacher was cool about it.
Yeah, I
The
hope
fact
so.
that he's 30 minutes late.
All right, so this is computer
Sorry, I
architecture.
was sitting in the wrong class.
This course is going to be a little different, actually probably vastly different than your previous ones, because in this one we're going to talk about how do you actually build a computer, and we're going to talk about it actually from a low-level design. How do you actually build the transistors, the circuits, put everything together, create a processor, and then how does your processor actually execute the code that you write, and what does your compiler actually do to translate the code you write into assembly so it can actually be executed. So this is going to be a lot of low-level stuff. But first off, we are not electrical engineers here, so we're not going to be doing too much in the hardware. But I'm going to get you at least low enough so that if you ever had to talk to an EE being electrical engineer, you could at least understand what they're talking about and be able to interface with them. So from a software standpoint, it's very useful for understanding how the machine works. From a security standpoint, you also need to understand the machine works because a lot of vulnerabilities come from the fact of how a processor actually operates and how your machine works. So this is a very important course for both of them. I think this is the first time I have two cybersecurity majors in here, so I'm interested to see how it turns out for y'all. Let's work on. Okay, so computers are pretty complex devices, although they really are pretty simple in a way because you have a CPU, which is really just a bunch of transistors etched on a silicon connected via some wires. That's all it is. Of course, by a bunch, I mean billions of transistors inside this tiny little thing, and then you have wires running around connecting all your devices. But that's all it is essentially, is transistors on a piece of silicon. Okay, so we're going to talk about how do you go from your C code to your execution. I probably haven't done that too much. Has anyone here done assembly before? Maybe one person. Okay, good. So we're starting to transition to no one's done assembly beforehand. So we are going to go into how assembly works and how you actually write it. And we'll go into more depth about how you take your English-like C code and how does it translate into something the computer can execute, because the computer does not understand English at all.
Not yet.
Don't get me on a tangent now. Okay, logic. So computers execute your program set of instructions. Y'all are probably used to this. It executes exactly what you say. These instructions they execute are very simplistic, far simpler than what you write in C code. They're really just signals, and they're usually executed in type of a step. Y'all probably have heard of the clock cycle. And a clock cycle is basically one iteration of work that gets done. So we're up to, what, 3 gigahertz, 2 gigahertz? So that means about 3 billion steps per second that the computer takes. And some instructions will take multiple steps, some do not. For example, add usually takes 1 step. Multiply can take 20, 50 or more. And of course, other instructions will take way more steps. But in general, they take at least 1 step in order to execute. And we'll figure out why that is in this course. Okay. All right, the computer revolution. So this, of course, is a big thing that happened, when did this start happening? Probably early 1900s, which is still pretty young when it comes to science. Has anyone heard of Moore's Law?
Yes.
Yes, what is Moore's Law?
Well, in order for computer chips to get faster and faster. Oh no, this is about is this the speed of computer processors?
They usually relate it to speed, but that's the misnomer.
Okay, because I was going to say the other part is like transistors are getting closer and closer and smaller, but after a certain point, quantum mechanics comes into effect and you can't really get any smaller than that.
Okay, so Moore's Law is simply about transistor count.
Just about transistor count.
It is the number, all it's saying is every 18 to 24 months, aka a year and a half to 2 years, the number of transistors you can fit in a set area will double. So it's about density. Now, if it's doubling, what type of growth is that? It's not linear, is it? is exponential. So exponential growth and density, which is a lot. And this law was written he came out with it in the early 60s, and so far we have maintained it. And we will probably still maintain it for a good 5 years. People say it's going to keep breaking, but it has yet to fully break, in my opinion. What that has broken is they'll say that when you double the transistor count, you should see a doubling in your performance. Moore's law has nothing to do with performance. It's about transistor count. Now that is true. We don't double performance now every 18 to 24 months. That's not happening. But we'll talk about that actually probably today of what's going on. Computers everywhere. Automobiles, cell phones, the Human Genome Project, World Wide Web, search engines. They're everywhere nowadays. I just wonder when they're going to start putting it inside of us. I wonder what they're going to run off of, though.
There's been many a Doctor Who episode over that.
Yep. Might get bad. All right. There are different classes of computers, and that's important to keep in your mind, these different classes, because your architecture will need to reflect the class of computers. So there's three big ones. The first two, personal computers, those are the ones standing in front of you, my laptop. Server machines, which are more network-based, high capacity, performance, and reliability. Actually, right off of here, I put some bullet points, but what's some big differences between a personal computer and a server machine that you can think of? Right off the bat.
Can't servers like hook up to multiple computers?
Yes, although our personal machines can do that as well.
Not as effectively as.
Not as effectively. So a server is designed to hook up multiple machines. Okay. That's a good one. Anything else?
Do server computers usually have like a monitor and stuff, or is it just kind of like?
Some of the servers we have back there have no monitor. It's just a box with an Ethernet cable.
Pretty much personal computers useless without a monitor because.
Yeah, so you have a lot more inputs. Okay. So that was a good point. A server is very geared towards serving a lot of different people at the same time. What's a personal computer better want to serve at?
One person.
One person. All right. So here's the big thing. We'd like to talk about latency and bandwidth. Latency is how long it takes for you click on a button, how fast it comes back. Bandwidth is basically how much you can take care of at once. Which goes with which?
Bandwidth goes with servers.
Yeah, bandwidth goes with servers. If it takes a little longer to serve it, you have slightly lower latency. In general, that's okay as long as you can go ahead and serve, all your users that you have. But with the personal computer, does anyone want to wait?
Nope.
No. So you don't really care. You don't really care if 3 people can use your computer at once. There's only one person using it, so it's geared more towards latency, and that actually has
3 people trying to type on one keyboard.
Yeah, so there's a different aspect here. All right, supercomputers. Okay, actually, the book comes out with 4. I usually stick with 3 because supercomputers are kind of merging with server machines. High-end scientific, very capable, but represent only a very small fraction of the overall computer market. Have any of y'all ever looked at top500.org? Nope. Which country do you think has the biggest supercomputer?
Japan.
Good guess. They're usually up there.
You see the biggest?
The most powerful. Let's do biggest, most powerful. Let's stick with most powerful.
China.
It's China.
Of course.
Mm-hmm.
Should have guessed that.
Yep, China.
They basically build it.
They did what?
So they basically build everything.
Put together a life.
Green 500 now. Wow. Oh, they're not going to give me the list. Here we go. So, yep. Number of cores. What's that? 10.6 million cores. Wow. Oh man.
Oh wow, Switzerland's on it. Go Swiss.
Oh yeah, the Swiss.
China holds the
Number
first 2.
3. Yeah, but nobody gets Switzerland. Switzerland's up there.
Switzerland's down.
They're like, oh, we're for everybody. Just kidding.
What's that?
And Japan.
Finance, even the financial centers, they've always
Then
been
the
at work
US.
in technology.
That's true.
We need to get better.
Nothing else is even
Yeah, but
close
we
to
have the
China.
next.
Well, there's some interesting
5 to
there's some
8.
interesting numbers here. What is it sorted
Well,
by?
ours-
Well, it's really sorted by T-flops, tera floating point operations per second. Talk a little bit more about that, but we'll just say how many times can you add a floating point number per second? We'll just say, for the sake of argument, that's what they're talking about. It's not exactly, but just try and keep it
Oh
simple.
my gosh,
Yeah, right?
that's a lot.
It's a lot.
93.
What I love is the number of cores here. It's got 10.6 billion. Number 2 has 3 million, and 33. So that's roughly about the same. But then this last one, if you look at the T-flops versus number of cores,
It's a lot more.
each core is doing a lot more work, right? Yeah. So that's a little bit of a difference there. Maybe some.
Switzerland's coming up there.
They just need some more cores, and then they'll be better than
No, because that's the whole.
My
adding
other
more
my other
things
favorite
doesn't
thing is look at how much
necessarily
power
get
these things
better.
take.
Oh my gosh. Okay,
Yeah, so it
what's
takes
Switzerland's-
15.3 megawatts. That's basically a power plant
Oh my gosh.
hooked directly into this machine.
one.
Right,
one.
that's basically what this is.
We
Just-
just need 2 power
What I'm
plants.
seeing is that Switzerland is having like a higher quality.
All right, here's another thing. Look at what's being used. The Sunway NPP. Anyone heard of that?
No.
No, that's because China made that. What's next?
Intel.
Xeon.
Which is Intel.
Okay.
Intel.
Intel.
And then Opteron is AMD.
There's
Oh, and then finally
NVIDIA.
IBM comes out with their chip. This is probably an older machine. Where's this one in? Yeah, so this is an older one when IBM was pretty big with their Blue Gene. And then back to Intel.
Intel.
Now,
Intel has some fun.
these machines are actually using what's COTS, or commercial off the shelf. These processors you could buy these, except for that whole Sunway thing, silly thing. But yeah, these are commercial off the shelf. That's the way we've gone, is you can buy most of these machines, and if you really had the time and money, you could probably piece this together in your, maybe not quite your garage, but if you rented out some space, maybe you could do this.
You need
An
the money though,
outdoor
since it has a lot of
garage.
Yeah.
Get a
power.
big one.
And you bought your own power plant, right?
Yeah, you have to buy a power plant first.
Not for the Swiss.
Not for the Swiss one. Yeah, the Swiss one.
Throw out a couple solar panels. You're good.
It might be a while. Also notice, good morning, Jonah.
Morning.
Oh, of course you're late.
Notice how the power goes down and then it kind of, skips back up. So the power and the number of cores are actually jumping around quite a bit here while you're sorting by T-flop. So I wanted to show you that different processors have different capabilities power-wise, as well as different power consumptions in order to maximize their
I
performance.
mean, Japan has like the lowest power input, but at the same time, Switzerland uses the less.
Yep,
least amount of
Japan.
cores.
I think this one,
Oh my gosh.
this might have been their,
That is a lot of cores.
yeah, Marine Earth Science and Technology. So this machine is very interesting. If I remember correctly, this is the one they built in order to simulate the Earth.
Oh, fun.
It's interesting.
I want to know just
I
what all
mean,
their.
like tectonic shifts and plates and things like that?
Yeah, the whole thing. Yep.
Sounds like a lot of.
I kind of want to look at it now.
Well, there you go. Top 500. Okay, so supercomputers, all about performance. Do you think they care much about power?
No.
No. On the other hand, your phone, does it care about power?
Yes.
Yes. No one wants battery life. So we have another objective here with embedded machines. Now, how much power does your processor take? So we got all these demands now, right? We want low power consumption, high performance, and hopefully cheap, right? You get those three. Well, we'll see what we can do, right?
We'll give you power
The
consumption.
point I'm hopefully you understand takeaway here is architecture is all about trade-offs. We can do different things, but you're going to have to start giving up something else in order to have what you want. If you want it cheap, it's probably not going to be super powerful, and it might be, if you want it cheap and low power, it's not going to be powerful. It's one of those like choose two options going on here.
I was always taught not to settle.
Nice. Nice. Okay, this graph's a little old, but wow, this graph's actually really old. 2012. Okay.
Only in computer
Yeah, problem is
science
this-
that-
Oh, this is old. This is old.
Only in computer science.
The point here is that PCs have actually been going up steadily, and even with tablets and phones, it's still just going up steadily. It hasn't really knocked into it too much. There was a small dip over here, but it's coming back up. Cell phones, well, and smartphones, I hope you can tell, have just, as well as tablets are still pretty good. Yes.
What is this measure?
So this is years, and this is basically the number of devices sold.
Oh,
Oh, wow.
In the million?
I forgot what. Yeah, in the millions. I'm assuming that's it. I had.
Yeah, only.
This is
What
really-
Coming does,
This is
though.
really terrible. It was not labeled access. Thank you.
Yeah.
Note to self.
No labeled
Update.
access. There's no like idea of whether it's millions or is it really just hundreds? Because that's a little ridiculous. And I think that's
We've only
false.
sold 390 PCs. Y'all are part of the elite now. in case you didn't- All right.
What middle?
So tablets and cell phones are taking over, which means that companies are now trying to gear towards embedded machines, which means they're more concerned about power than they're more concerned about power than they used to be. Still concerned about performance, but power is becoming a bigger and bigger issue. All right, personal mobile device, battery operated, connects to internet. They want to be hundreds of dollars, which is cheap, by the way. Smartphones, tablets. Hey, electronic glasses. Did anyone ever have those? The Google Glass? Nope.
What?
No.
They like
That was a thing?
Never had that?
I didn't know!
Yeah, it's
I would
cool.
have gotten a pair.
around
so
and look normal with it.
That's so cool! I want a pair now.
Yeah, it's Google Glass. No one had
eBay.
that? Okay.
Is it Google Glasses?
Did anyone jump on the smartphone bandwagon?
Ah.
I have a smartphone, but
I mean,
I was about
smartwatch.
to drop.
Sorry, smartwatch.
My brother has one.
Smartphone? Does he enjoy it?
Yeah, he enjoys it. He gets really dramatic with his whole when he turns it off. I
The
don't know
running
why.
joke at Google was, now that we have the smartwatch, the next thing will be the smart nail. It just goes over so you don't have to look over as much. You just push. Anyways. All right. Mobile devices, again, taking over. Cloud computing is a big thing. It's gotten even bigger nowadays. I'll try and, I guess, explain this a little bit.
It's on
Explain
eBay,
cloud computing
so
a little better.
it's actually
But the
probably-
idea, have any of y'all done any AWS or Azure or anything like that? Nope. Okay.
Blank faces.
It's real. No, it's fine. The cool thing about
This.
cloud computing is that you pay AWS and you just basically rent their servers
Oh, I'm
and
doing
rent
that
their
right now.
capacity and rent all of their
Cloud
architecture.
Um,
And we'll get more into
user
that
interface
later.
development. Every time.
All right. So what we're going to learn, how we translate to machine language, how the hardware executes them. That's a big one. How does the hardware and the software interface with each other? That's a big one. We have hardware. How does it actually interface with the programs, the software we have written? Magic. I'm going to now put no longer it's hand waving. It's no longer magic. Let's see. What determines the performance of a program? It's actually not very intuitive, but once you learn it, it's pretty simple. Or I think it's straightforward. It's not simple. How can we improve it? How do we improve performance? And then what, of course, is parallel processing. All right.
I wasn't laughing at you. There's something on sale.
We found the Google
It's on
Glass.
$12 chicken.
3 P's for performance. Whew. This is going to be very common the whole time when we talk about performance. There's usually 3 ways we do this. The first one is standard parallelism, and you're used to this. You have one core. Let's just add a second core and try and make it go faster. Sure, why not? Pipelining. Anyone know what pipelining is? Y'all have all done it. So here's the good analogy. If you go to do your laundry, do you wash your clothes, dry your clothes, fold your clothes, and then put the next load of clothes into the washing machine?
Nope.
No, what do you do?
Wash them, put them in the dryer, put new ones in the washer.
So you're pipelining it, and so what you're doing is, while one of your instructions is executing, your multiply, for example, you go ahead and start the other one right behind it. So then your throughput will increase. Your latency doesn't decrease because it still takes you that long to get the whole thing done, but you can get more of it done at a certain time. So that's a very popular way to go about it. The third one, when all else fails, you can't do parallelism, you can't do pipelining, you do prediction, which is actually just as bad as you think it is. Oh, we're doing a multiply. All right, we're going to guess this is the answer and then run with it. And if we're wrong, then we'll go back and figure out how we can fix it. Doesn't work too well. Well, it doesn't work too well in certain situations. There's actually one situation where it works very well. We'll go into that with branch prediction. All right, so those are the 3 Ps. I want to ask you, how can we improve performance? Think of those 3 first. Another very common thing, small is fast, big is slow. Pretty much without fail, if the chip is small or your memory is small, it's going to be pretty fast, but you don't have much capacity. If you won't make it big so you can have a lot of memory, it's going to be pretty slow. This is very common. One of the big problems that people or students have with this course is you now have to think in parallel. Beforehand, you've been thinking one step at a time. Your program goes down one at a time. We're going to use something called Verilog in order to design our processors, and you have to understand that all of it is happening in parallel. So all the code you write is happening at once. It's not just doing one thing at a time. Yeah, so that's Verilog. Okay. I think you all know me.
I think you need to introduce yourself again one more time.
Just one more.
Thanks, Carl.
I'm not sure. I can't remember. No.
Who's this guy?
I don't know if you like. It's just like it's hard to remember.
So everyone go on GitHub and be ready to give me a username. I'll stop probably after the syllabus and make sure everyone gets on GitHub so we can submit everything. And let's go ahead and go over the syllabus.
Syllabus.
I have to go over the syllabus, okay?
Syllabi.
No, it's just
I'm already in the GitHub. I'm good.
No, you're not.
No, you're not.
I see it. I can see it
Oh,
now.
let me